computer. All right. Okie dokie. Okay. All right, I'll get us started here. We're at module 9. And as we're moving on through, just want to remind everybody we're going to be coming down to a point where I'll be turning you loose on some projects. But this week we're going to look at a couple of interesting cases. And the first one is the case of the naive Bayes, and that uses the mandrel file from the Foreman text. And that is going to be chapter, I didn't get vital source up, so I can go, let me get vital source up. I think it's going to be chapter, take a look at it real quickly. What we're going to do is we're going to see how we use data science to deal with data science techniques to deal with this, with the issue of what we call big data. Now, so you'll want to go over to the, you'll want to get the Foreman files. Those are in the files section there in Canvas, and it's going to be chapter 3, okay? And we'll talk about that case a little bit today. And again, as I said, it's an example whereby we're going to be using management science techniques to deal with big data. And we'll cover it here in just a sec. So let me get my vital source up and going so I can walk you through the textbook. As I said before, pretty ingenious use of Excel. Let's see here. And we're going to see that we're going to work with tweets basically. And oh man, this is password day. That's Monday, is that? All right, hang on a second here. This is, no, I'm logging in. Caps lock. Okay. All right. All right, I'm going to have a fight with vital source to log into them today. So hopefully you'll have your book with you. But chapter 3 is what we're going to be working with. And I'll pull up the file. It's in the chapter 3 of the Foreman files. So you'll want to grab those. And that's in the files section of Canvas. And it's called mandrel. I want to talk about it a little bit. The in this case, what we're going to do, and there's the mandrel case. I'm going to copy that and throw it on the desktop. We're going to take a set of tweets and try to find out if those tweets have anything to do with a product that these folks at MailChimp offer. And when you open up the file, you'll see, okay, that he's got a set of tweets. And I don't know, I think there's 120 of them, whatever it is, I don't remember exactly. But as you can see, these would constitute what we call big data because they don't necessarily easily fit into a table or into a database. Over in chapter 3, it looks like I'm going to get to do this the old-fashioned way. He talks about using probabilities to determine whether or not something in one of these tweets is talking about their product or not. Okay. Now, he's going to be using a data science technique because we're going to be using Bayes' approach to probability. Now, before I get too far into that, I also want to note that we're going to be working with a case also. Now, this second case is out of the big textbook, and it's called single arbitrary. And what we're going to be looking at in that case is network analysis. Now, let me say this. Network analysis would be in itself just an entire course. So we take a look at it, but again, remember, this course is an introduction to management science. So we're looking at a lot of different pieces of it, and network analysis, queuing theory, that like I said before, itself would be just a course in of itself. And the single arbitrary, I have there's a file over there in chapter 11 in the Anderson text, and you're going to find that file is in the Anderson. The coverage or the discussion of that is in pages 525 through 29, which is in chapter 11 in the Anderson text. And the file in there, single arbitrary, means we have a single channel of incoming people that we handle in a queue. A queue is really nothing more than a line, and then the queue is really the wait, how long people have to wait, etc. You'll see that as we walk through the chapter. Now, I'm going to ask you to change some variables there using the goal seek, and then we'll talk about that a little bit more, and we'll look at some more network analysis cases next week. One of the things in single arbitrary that will be a little bit different is that we're just going to limit our usage to goal seek, okay? And you'll want to get that file, is over there in the chapter 11 in the files of the Anderson textbook. Now, and I do apologize about the thing with the vital source. I don't know what's going on with those people, but I don't want to take the time during class to reset a password in that junk. So if you start over there in chapter 3 of the textbook, okay, and that's page 77, he gives you a bit of an introduction to what we call naive Bayes, and this is an approach, and it's called naive for a very simple reason. That is, the assumptions about the events that occur is Bayesian approach says the events are basically independent. And I'm going to show you that here. And I'll pop over here. No, that's not the one I want to do. Show here just a second. Oh, what a morning. Okay, I'm talking interesting. Okay. No, I don't want to show that. Okay. Well, this has been just a stellar start, hasn't it? Maybe this is what I'm after. Now, let me put it like this, okay? If you've had your stat course, you should have had some cover. You should have covered some as regards using probability theorem. In fact, if you use, for example, a Gaussian distribution, i.e. the so-called normal curve, you assume that you're working with basically a distribution that about 2/3 of all observations fall within one standard deviation above the mean versus one standard deviation below the mean, and then accordingly out to 3 sigma. So when we work with statistics and we assume that they are what we call parametric, we assume that they fit that. Now, if we work with statistics that we would call non-parametric, we'll use some techniques like if you, in your stat course, use chi-square. Chi-square assumes that the distribution is non-parametric. And so I want to grab this. I think this may give me exactly what I'm wanting to talk about. Okay, here we go. And let me put this into full screen, because I want to spend a little bit more time on the background for what he's doing here, so that you understand and understand that naive Bayes has kind of taken a foothold. When we work with probabilities, one of the major questions we always have to address first of all is if we have a sequence of events, if those events are independent or dependent. In other words, we have event A, event B, event C, etc. Is B dependent upon A? In other words, if A does not occur, B can't occur, etc. And that's a big assumption. A good example would be in sampling. Let's say that you have a hat full of red beads, and it's got 100 red beads in it. And we all know that when you get ready to sample and you pull a red bead out, the odds are 1 in 100 or 1% you're going to get a red bead. Okay? All right. Well, no, not full of red bead, but full of all various colors of beads, excuse me. And the odds are 1, and I have 100 different types of beads. Now, if I pull the red bead out and then I sample again, I'm going to be changing the sampling parameter, because now I'm only dealing with 99 objects, not 100. So that's what you call sampling without replacement. And sampling with replacement versus sampling without replacement is different. And it's based upon your assumptions about the dependence or independence of the events. So naive Bayes, and Bayes was he was a mathematician who said, you know, there are a lot of things that we really don't know whether or not they're dependent upon them, because there may be some extraneous or other forces or factors or variables that come into play. So naive Bayes operates from the assumption that every single event is independent. Okay, and that's why I've got you there. I show you this is this chain rule where when they're independent, we figure the probability by multiplying, and that's was a note there, the chain rule of probability. So we're assuming that those probabilities are multiplied. Okay, otherwise those probabilities would be added up. Now, he's going to use in this chapter 3 Bayes' probability to build an artificial intelligence model. Okay, and that's why I wanted to have you go through this text, especially this case, for the simple reason that it's a very classic example of a way that we can use management science to deal with what people call big data. You say, what are big data? Okay, let's go back over that. Big data consists of any kind of data that's out there that's not structured. You say, what are you talking about? Well, I'll give you an example. Okay? These are tweets. Tweets are unstructured data. They're not easily put into a table. They're not easily categorized. They employ language which has nuances. They employ special characters. Big data would also be things like folks' recommendations at Yelp, or likes or dislikes at a Facebook page, data from sensors. And we have all of this stuff coming in on us, especially from social media and from things like email. And so we want to try to find out, how do I lasso all that stuff, get it, and then get it into a format where I can do something with it and I can figure out what it is I need to do. Okay? So in this case, these folks, he was working for MailChimp. They're trying to determine whether or not a tweet is about their product or it isn't, and they're going to use Bayesian probability to do that. And then we'll clean up the data first, and then do the probability work. Okay. Now, they walk through a decision rule map. And as I mentioned here, you assume there are 50-50 odds that a tweet is about their app or it's about something else. Everybody with me so far? Now, everywhere I go that people have anything to do with working with what we call big data would tell you that 90 to 95% of the work is just wrangling the data, getting it into some way I can use it, i.e. into tabular form, putting them into a table so that we have columns that are dimensions or characteristics or variables, and then we have data or values filled in each one of those so we have a complete record. The bottom line is that working through all of that is an enormous job. And I went through a program at Johns Hopkins a couple of years ago. They were giving us all types of data that the data sets really had to be wrestled with to get them into some kind of usable form so that we knew what we were observing or working with. These are data that often are legacy data. And then there are also some modern forms of things created, especially with things like social media. So what he's done here is he said, okay, I'm going to use naive Bayes to determine whether or not a tweet is about our product or not. So they're monitoring Twitter, and they're going to go out and scrape a bunch of those, throw them into a spreadsheet, and start to take it apart. And that'll be kind of the data cleaning and scrubbing that we're going to see. Now, he's also going to normalize those data by using some adaptive smoothing, okay? And we'll normalize the data by adding a smoothing constant so that if we use a large number of bits of data, that the probabilities we prevent the probabilities from becoming so small that they're really almost meaningless. So we add that, we put in that smoothing constant, and he shows us that probability, okay? And it'll be greater than or equal to this probability that it is the other. So you'll notice here at the top, he's got the probability that the word deals with the app, the probability of word 1, then word 2, and then it's greater than or equal to the probability that's about something else. And we'll add a 1 on that to create a smoothing constant. Then we're going to convert those products, and then we'll start to use some Excel functions to we'll build a predictive model and determine whether or not the tweet is about that company's product and its mandrel. Does that make sense? Yeah? Okay. The easy part is conceptualizing this. The hard part is cleaning the data. So over in chapter 3, he's going to walk you through just a little bit of information about the approach he's taking, and he's using a form of textual analysis. He talks about signal versus noise. He uses that phrase. Signal is when I'm tuning it, say for example, if I'm tuning a radio, and I'm going to hear a lot of static till I hit a radio band that's close to me, etc. And anything between that is going to be noise. It's going to be that fuzzy sound that you hear. But when I hit that, when I hit that radio station's call, I'm going to hit that frequency and I'm going to get a signal. But every piece of data has signal and noise. The question is how much noise in there, and the noise is just random stuff that's out there. It's probably about as good a testimony as the fact that we live in a fallen world, because nothing has a perfect signal. Nothing does. Everything has a little bit of noise dropped into it. Now, here in the bottom, these are the Excel functions, okay? And you'll notice that we're going to be using quite a few database types of functions, okay? And then we're going to take those numbers when we had the smoothing constant, and then we're going to turn them into logarithms. So they turn them into truly natural numbers so we can compare them. And we're going to do that using the E constant. And then we're going to use some more conditional formatting, conditional statements. We'll use a VLOOKUP. But you can see, and we'll talk about how he goes through that process as we walk at it. Go there on page 79, he talks about a thing called the bag of words model, okay? And the bag of words model is very simple. It says, okay, I've got this, I've got a book, I've got a paragraph, I've got a tweet, I've got the script of a movie, I've got the lyrics from a song. That bag of words constitutes a whole, and it has parts, and within those parts, that's what creates the whole. So I grab a bag of words and I assume that the context has meaning, okay? And as we try to discern, okay, what is the meaning of it? What is it? We go back to the question of, okay, if I'm looking at the Gettysburg Address, for example, what am I really looking at? Am I looking at a funeral eulogy and memorializing what had happened? Is that what Lincoln was doing? Was Lincoln stating a different kind of interpretation of the Constitution, which a lot of people say that he was? What exactly did he mean? Well, we never got the chance to ask him those questions, unfortunately, and never had the opportunity for him to sit down and write a biography and explain what he said, which is quite unfortunate, because as we've looked at his address, he's had one key phrase that he inserted in that, okay, which is completely antithetical to anything that had happened in our country prior to. And the phrase is one you know very well, and it says a government by, of, and for the people. The United States was not established as a democracy. It's a republic. And we elect people to represent us. That's why you have a thing called the Electoral College. The Electoral College means if a person carries a certain state, they have so many votes. In the old days, the Electoral College was there to make sure that we didn't elect some crazy person as president. And so the Electoral College people who represented the Whig Party or the Democrats as the Whigs went away, or the Republicans, they would cast a vote. But if they thought they had the right, they were not bound by law to vote for a particular person. Some states passed laws that tried to make them do that. But the whole point is, in Lincoln's address, he uses some words. And within the context of the Civil War and within the context of the Emancipation Proclamation, he changed how people have interpreted our country in terms of its political structure, because he was inferring a democracy, not a republic. The people who founded our country were afraid of the mob. They were afraid of the common people. They wanted to, they were afraid that this vast group of people who are uneducated and out on the frontier, who knows what kind of craziness they do. So they built in some what they thought were safeguards, but they also built in safeguards to stop the country from being run by just a small elite group of people. So this whole bag of words, this is an approach that people use when they try to do textual analysis. Then he walks you through over there in 70 and page 80 and page 81 when he talks about probability theory, and he is right. It's the world's fastest introduction to probability theory you're ever going to get. But when you think about it, when we're doing this, this is an exercise in probability. Was the tweet about the product or not? And so we're going to build a predictive model to be able to do that. So as you walk down here through, as explained, I walk you through some of the, I take you cell by cell by cell in that first row, what we're working with. And this will become more apparent as we go through and we start to take a look. Now, this issue with the mandrel also creates some situations for us, okay? And the issue of type 1 and type 2 error, okay? And let's talk about this for a minute. You say, oh, this sounds a little bit like stat. Yes. Here's the basic question. Let me put it into a full view for you, okay? Okay. We have type 1 and type 2 error. We have type 1 error. It's called a false positive, okay? Now, let's say that you're going to the doctor and the doctor says, we've found a lump and we want to look at it. Or let's say the doctor says, we've found a spot on your lung. We want to see what it is. Which would you rather have? A test that will give you a false positive or a false negative? Well, most of those diagnostic treatments tend to fall in the area of a false positive. Is it better for you to believe you have cancer, or is it better for you to have cancer and not know about it or not believe it? And that's really what you're talking about when we talk about type 1 versus type 2 error. And then you can see that we have the false positive, that's the type 1 error, and you can see they're just almost a mirror image of each other. Type 2 is a false negative. And it's a balance between each of those. So if we have type 1 error, okay, is this spam that we're getting, or is it actually about our product? We classify too much as spam, and so we cut out a whole bunch of email and we simply say, okay, this is spam, and we dump it off into a file. If you're using Microsoft Access, if you're using Outlook at school or Outlook anywhere, you'll notice that you'll get, at least here at OVU, you'll get a clutter. And it'll say, here's all this clutter that we received. Do you want to keep it or not? Because they'll look at it and say, this is questionable because based on your traffic and patterns, it just doesn't look like anything that's of importance to you. So this is the problem that they're trying to solve and trying to build a predictive model. Okay? And we talk about alpha error, beta error, type 1 versus type 2 testing, the errors that get introduced into that. And it's a balancing act between the two of them. And it's always a strategic choice. Which one of these is worse for a client of MailChimp? To have too many tweets classified as part about the app, or for them, or is it okay to have too many of those tweets that are classified as non-app tweets when actually they're about the app? Does this make sense? Yes? Okay. That's, as I said, we're using a management science technique here. We're using probability theorem, okay? And then we're also going to start to work a little bit with the data. You know, when we use the optimizer and we choose an objective function, and then we choose the changing variables, and then we build constraints, we're engaged in an exercise we're engaged in a probabilistic exercise simply because I say, well, here are the variables that are important for me to change. I've selected these variables. They need to be changed. Have you selected the right variables? You hope so. experience will show whether you have or not. Have I built the constraints properly? Another exercise in probability. Well, it's the same story here as we're going to look at this case and see how he qualifies, or pardon me, how he classifies it. But he's going to create a little artificial intelligence app for us that will machine that will let us see whether or not the app within a reasonable degree of error, whether or not a tweet is about their app, i.e. their product, or is not. Okay? So again, this is all about using a management science process. In this case, he's using error. He's using probabilities. Now, this week we're also going to look at the single arbitrary case. And if you go and you take a look at your textbook, you're going to see over there that single arbitrary deals with network or queuing theory. And one of the things that we do and we deal with that is, what's the probability of the arrival time? Let me open up that file for just a second. I've got it on my desktop, I think, here. And we can take a look at it. I believe I opened it up. I've got Mandrel. Well, and I think single arbitrary is going to be back. I think it's chapter 11. I'm probably wrong. No, it's not. Well, oh, I know where it's at. I've already got it up here for you guys. Sorry. Scroll down to the next module. Here it is. Now, let's download it for just a second. I apologize. That's why I stuck that key there so I didn't have to push around the book. All right. Now, throw that on your desktop and then open it up. Okay. In this case, we have what we call a single channel model with arbitrary service times. What does that mean? Well, what it simply means is this. Let's say that I have an ATM, all right? An ATM, and I don't have any other ATMs around. It's not part of a branch banking facility. I just have an ATM, okay? I have a single channel model. In other words, the queue, the line of people, the customers who come in, there's only one way in to do it, okay? Now, when we talk about arbitrary, then we're saying, okay, we have an arbitrary service time, okay? And that's set up for how long we'll let it function. You say, oh, that's not true. And I go to an ATM, it works if it, oh, yes, it is. If you take your credit card and you put it into, you go to an ATM and you stick your credit card in there, sit and wait about 5 minutes and see what happens. You'll start to get all kinds of messages. And some banks, if it sits there, will simply eat the credit card. In other words, bring it back on into the back of the machine and tell you need to contact your financial institution because they think you're efficient. You don't have an account. So we assume there's some arbitrary service times. It's going to be the same thing as in a car wash is a good example. People bring their car in, okay? They drive in. You choose the type of wash you want. And the type of wash you want is determined by, you want to have the thing washed and special wax and rinse and tires and all of this. Well, that sets up an arbitrary service time by the fact that you chose those, and that automatic car wash is only going to do what you've told it to do, and that is give me the full treatment, or I just want to wash, or whatever you'd want to do. But it's a single arbitrary line. Now, one of the things we try to calculate when we deal with any kind of queuing system, okay, is we work with arrival times. And Notice that we have Poisson arrivals and then we have arbitrary service times. You say, what do you mean by that? Well, let's go back to the car wash. You and I both know that if we sat outside a car wash and we watched, there will be certain times of the day when cars will get washed, people bring them in, and then it settles down. And then you'll have another peak time. I can also tell you, and you know this as well as I do, after 2 or 3 days during the winter time, if it warms up, people take their car to get them washed. So we know about the arrivals in the sense that it tends to ramp up and kind of plateau and ramp up and kind of plateau. And then we have arbitrary service times. If you have an automatic car wash, the car wash doesn't know any different. It just says, okay, well, you ordered the full thing, so that's going to be 4 minutes or 5 minutes you're in here. You order just to wash, that'll be 1.5 minutes. And to control that, what do? Well, they have you drive into the car wash, and there's a thing that locks your wheels, and you put your car in neutral, and you go through the car wash. So they have control over that. If you go to kind of an old fashioned car wash, you get people out there, they're putting quarters or whatever they're putting into, and the sprayer goes, and they use it, and then they buy a few more minutes. There's nothing arbitrary about that at all. The hope is that you'll just keep feeding quarters, and they'll make a nice profit. Okay? So you'll want to take a look at that. And in this case, we'll be using the single arbitrary. We're going to be a single channel model with arbitrary service times. We're going to be dealing with just the most simple of all of these models. And you'll see they get more and more complex, but you can see here we're dealing with probabilities. And note this is what we call the operating characteristics. And we start with the probability that no customers are in the system, the average number who are waiting, the average number of people who are actually in the system, the average time they're waiting, the average time they spend in the system, and the probability that an arriving customer has to wait. Folks like hospitals that operate emergency rooms will staff the rooms according to what they know to be patterns of behavior on the part of people. 4th of July is one of those times when they guaranteed there's going to be gunshot wounds, people who held a Roman candle too long, somebody who threw a firecracker at somebody's face, on and on and on. So they ramp up. They ramp up on New Year's Eve because they know there will be people out drinking and driving. They ramp up at certain times because they know a lot of the automobile accidents occur during a certain time frames during the day. Well, that'll be something for you to take a look at as you work through that. Pages 525 through 529 deals with single arbitrary. Okay? Let's go back for just a second now, and let's take a look at this mandrel. Okay? Now, we have these tweets, okay? Now let's start with the first one on there on A1, okay? And we want to say, okay, we know these are about the product. Now what they're doing is they're doing a little bit of what we would call an ex post facto analysis, that is after the fact. They're going to try to say, okay, I'm going to have a set of tweets that I know are about mandrel. I have a set of tweets that I know are not about mandrel. I'm going to clean them both up, and I'm going to try to run a predictive model to see if I can tell, yes, this is about mandrel, this is not. So we can ignore this tweet, or this tweet's something we need to take a look at. Got me? Okay. Ex post facto means after the fact. The best example I can give you is every time a hospital has a mortality incident, somebody dies, they have a panel who goes back and takes a look and says, all right, let's see what happened with this patient. They'll bring in the doctor, they'll bring in the physicians involved, they'll bring in the nurses involved. And it's not to cast blame on anybody, usually. It's to find out, could we have done something different? Did we err, or what happened here. Did the patient really die of what we thought they did? Okay. One of the things, especially with very, very young or very, 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 very old patients, is they're highly susceptible to infection. And if you're in the hospital and you have an operation and you fit a certain profile, you're very susceptible to getting an infection. If you get an infection, that can become a problem. Sometimes it can cost your life. Or especially younger, very, very young people, very, very old people tend to have problems. They'll get pneumonia. So we're doing an ex post facto, and we're wanting to see what happened. Are we sure that what occurred? And that's why we're using this model here. We've got these tweets about the mandrel app, and this is about something else. So let's look at this for a second. And then you notice we're going to do a technique here. Here's the app, and then we're going to start to clean the data. Okay? The first thing we're going to do is we're going to use the lower function, and I have all those functions listed there for you. But if you want to just see it, here we are, just click on the FX, we'll see, and it tells us it's a text function, and you want to convert the text to lowercase. You say, why would I do that? Well, when I strip everything down to lowercase, I take away a lot of implied and maybe even untenable meanings. We use capital letters, right, to signify a proper name. And so what we're going to do is they're going to strip that all down to lowercase. See that? Okay. And then the next, here we are again. And we'll go over here to, and here we're going to use a substitute. Now you can click on this, and we're going to do a test, and it will walk you through what we're doing with the app. So I've written that up for you there, and I have it posted in some of my scrawly handwriting, but you can also check that out as you walk through here and see. I want you to see this because it's just such an ingenious use of Excel. I've never seen anything like it in my life. So, but he's basically saying, okay, the old text, anywhere we find that looks like a comma, we're going to get rid of it. We're going to strip it out. And then we'll go to the next. And we're over here. Same story there. Now we're going to get rid of question marks. Now we're going to get rid of any other exclamation marks. A semicolon. Or we're going to work with commas. And then we have the whole entire tweet as it's cleaned up. That's column I. And he's going to do this same process with each of these tweets. And how many is it that they have? He has 150 tweets that are about mandrel. He has 150 tweets that are not. Okay? And he's basically cleaning those data up. Now he's going to clean them up in terms of using lettering, and then we've gotten all the extraneous characters out of here. We've gotten the upper and lower case. We've got the upper cases out of here. Then that's when we'll do that. We'll do the smoothing constant, which will be the 1+ when we get some probabilities, and then we'll use the log. So we've built a data model, which is what we've done every time. This is just a different type of data model, but we're not using optimizer here. We're using some functions that clean the data up a little bit for us. Then we'll use them. Then we'll compute probabilities, and then we'll add a 1, which is a smoothing constant, to keep them within the realm of something that we can work with. And he talks about that in some of the long division problems that you can run into, say, with Excel, and then we'll turn them into natural logs, and then we'll do predictions. Okay? So we're following the same pattern we would with management science. Now, what we're going to do after he works with each of these, and he creates this, column I is the cleaned up tweet, okay? It's now what we would call a token, okay? A unit that I can count or manipulate or work with. Then he does the same thing about tweets about the others, something other than Mandrill, same story there. He just uses that algorithm to clean that up. Then here he's going to start to look at these app tokens in terms of their length. And he's going to start with a space position 0, and he's going to say, okay, my token, how long is it? And he's going to use a conditional statement. And he's going to use the mid function where we look at the middle of a string, the middle of a string. And he's basically going to say, okay, we're starting from a 0 position. What's the length of that? This is probably the most complicated of all that he does here, because he's really taking each tweet and he's starting at a 0 point and he's finding, okay, where's the 0 point for it? Now let's watch and see what happens here. Here's the second one. And notice something. Okay? And we're going to use and that's the length that I want to find the spaces the characters for. He'll walk you through the book of that, and I've got some notes there in the case as well that lets you look at the length of these. You said, well, why is he computing the length? Well, it's very simple. Down here at the bottom, he's going to get a total number of tokens, and that's how he computes this probability. And if you look at here, you'll see the app token probabilities. There they are with their lengths. And so he takes each of the space position and walks through them. You'll want to look at my notes a little bit and also look at the book, because it's a little tricky to follow, but he's just simply saying, okay, how much space is allocated for each of these? What's the length? He does the same thing with the other tokens. And then he begins to build the probability for those. And you'll notice, and what he's done is for each of those tweets, okay, those tokens, that's where he adds the 1. So we've got these words in here. These words are tokens. Units that I count, units of measure, units that are important to me. And you can see he has these words and these email addresses and phrases that he's pulled from the apps. The tweets he knows are about the application. Now notice over here he uses the logarithm and converts these to natural logarithm data. And he does this, it looks like here he's going to use it. I think he uses he does. He uses a pivot table, and he'll talk about that there in the text. Now, I'm not going to spend a whole lot more time today because we're pretty much near the end of this. But what I said is on Wednesday, we'll come back and take a little bit of a deeper look at it. Now, I think that the single arbitrary case is is simple enough that you're really going to be able to grasp it, and you're going to be able to get what I'm asking you to do. Use goal seek and to alter some of the variables there. And you do want to take a look at that chapter. They're over in pages 525 through 529 so that you could see, get some background about queuing theory. Now, I understand that queuing theory can seem pretty boring, and it is boring until your stuff doesn't get there on time, or till you wait 45 minutes to an hour longer to get served than you should have, or you need a supply or a piece of equipment and you can't get it. Queuing theory is exceptionally important. It also works a little bit when you and I drive around town, and you'll notice that the stoplights have some different times afforded to them. They have timers, and those timers are set using queuing theory, knowing traffic flows. So we use queuing theory all of the time. And what they'll do in the text is they're going to walk you from the simplest up to the more complex. And we'll spend some more time on Wednesday taking a look at this. I'm sorry about the rough start to this. I truly am. And I would encourage you, before we come back, we'll go back over here, that you take a look at these resources I have for you in terms of the app tokens and getting their space positions, and then the app tokens themselves, the probability, how that's done, test tweets, the predictions, how that's done. I have notes there for you that will help you. There's one other thing that I would really, I've got some stuff in here about Bayes. I think this is a book about Bayesian analysis that I've read. It's been a while since I did, but I think here's one that you really want to think about. Now, all the time, the university is always talking about, are you integrating faith and learning? Integrating faith and learning. Okay, let me take just a minute, and then I'll go just a couple of minutes. Everything in the Bible, everything that we believe as Christians is based upon one test. Did a man named Jesus Christ live and die and come back from the dead? The Apostle Paul said, if he didn't, we are among people most miserable. We've bought into a lie. And worse, if we go around telling people that he came back from the dead, we're committing a blasphemy because we're speaking a false witness about God. So Paul says this is not good. So everything hinges on his resurrection. Now, I'm a pretty intelligent person, and I'm like probably some of you. You grew up in church. You made an emotional commitment to the Lord, make him the Lord of your life, but maybe intellectually you struggle with stuff. And I'm going to tell you this, there's a lot of stuff that the Bible says, all I can say is, well, it's a miracle. But there's one thing you and I can be quite sure about. There was no question among the people who were followers of Jesus that he had come back from the dead. None. And the Apostle Paul talks about the fact that 2 people saw him, the disciples saw him, 500 people saw him at one time. He was here for 40 days and 40 nights. It's not like he peeked in and said, hey guys, I'm alive, see you in a while. He was here, fully resurrected, having breakfast with the disciples, teaching them. And Paul states what he says there. I believe it's in Corinthians, or I believe either that or Colossians. And he says it for a reason. If there's anybody in the room who was there and says you didn't see him, raise your hand. And if Paul had been wrong, or he had been misstating the facts, he would never even made it into the canon of Scripture. So when you think about that, consider how Paul walks you through these numbers of people. 1, 2, a dozen, more than 500. And he said, many of whom are asleep, implying there are a lot of you out there. And if you're out there and you're a disciple and you didn't see it, let me know. If you look at the probabilities of that, whether it's dependent events or independent events, the probability that it's not true is so low, it's infinite. You have to be a fool not to believe it. So as you've studied here and you've learned, Christianity is grounded in history. There's no doubt about that. It's also grounded in a fact, the fact that what happened there happened. And so you and I can have confidence in that. Hopefully that will help you a bit with your faith. Well, thank you so much for the time. Thank you for letting me give you a mini sermon. I got you ready for chapel. I'll see everybody Wednesday online.